Hello, ladies and gents. Welcome to another episode of ML for Noobs. Now, we're going to be continuing Lesson 4 here. Lesson 3 is still doing its thing here. Wait, it's not Lesson 3. It's actually Lesson 4. Well, anyway, we're going to continue with the video, wrap that up, and then come back and revisit some of the results in a later video. Take it away, Jeremy.
So, Microsoft Excel. This is one of my favorite ways to explore data and understand models. I'll make sure I put this in the repo. And actually, this one we can probably largely do in Google Sheets. I've tried to move as much as I can over the last few weeks into Google Sheets, but I keep finding it's such a terrible product. So, please try to find a copy of Microsoft Excel because there's nothing close. I've tried everything. Anyway, spreadsheets get a bad rap from people that basically don't know how to use them, just like people who spend their lives on Excel and start using Python.
Google Sheets?
It takes thousands of hours to get really good at spreadsheets, but a few dozen hours to get competent at them. Once you're competent at them, you can see everything in front of you. It's all laid out. It's really great. I'll give you one spreadsheet tip today, which is if you hold down the Control key or Command key on your keyboard and press the arrow keys, here's Control right. It takes you to the end of a block of a table that you're in, and it's by far the best way to move around the place. So there you go. In this case, I want to skip around through this table, so I can hit Control down right, get to the bottom right, Control left up, get to the top left, and skip around and see what's going on. So here's some data, and as we talked about, one way to look at collaborative filtering data is like this. And so what we did was we grabbed from the movie lens data the people that watched the most movies and the movies that were the most watched, and just filtered the data set down to those 15. And as you can see, when you do it that way, it's not sparse anymore. There's just a small number of gaps, right? So this is something that we can now build a model with. And so how can we build a model? Like what we want to do is we want to create something which can predict for user 293 will they like movie 49, for example. Right? So we've got to come up with some way of, some function that can represent that decision. And so here's a simple possible approach. And so we're going to take this idea of doing some matrix multiplications. So I've created here a random matrix. So here's one matrix of random numbers. And I've created here another matrix of random numbers.
Okay.
Well, specifically, for each movie, I've created 5 random numbers. And for each user, I've created 5 random numbers. And so we could say then that user 14, movie 27, did they like it or not? Well, the rating, what we could do would be to multiply together this vector and that vector. We do a dot product, right? And here's a dot product, right? And so then we can basically do that for every possible thing in here. Got the dot product. And thanks to spreadsheets, we can just do that in one place and copy it over and it fills in the whole thing for us. Why would we do it this way? Well, this is the basic starting point of a neural net, isn't it? The basic starting point of a neural net is that you take the matrix multiplication of 2 matrices, and that's what your first layer always is. And so we just have to come up with some way of saying, like, well, what are 2 matrices that we can multiply? And so clearly, you need a matrix for a user, or a vector for a user, a matrix for all the users, and a vector for a movie, or a matrix for all the movies, and multiply them together, and you get some numbers, right? Like, so they don't mean anything yet, they're just random, right? But we can now use gradient descent to try to make these numbers, and these numbers give us results that are closer to what we wanted. So how do we do that? Well, we set this up now as a linear model, right? So the next thing we need is a loss function. So we can calculate a loss function by saying, well, okay, movie 3 for user ID 14 should have been a rating of 3. With this random matrices, it's actually a rating of 0.91. So we can find the sum of squared errors would be 3 minus 0.91 squared.
Oh, that looks familiar.
And then we can add them up. So there's actually a sum squared in Excel already, sum x minus y squared. So we can use just sum x minus y squared function, passing in those 2 ranges, and then divide by the count to get the mean. So here is a number that is the mean, the square root of the mean squared error. So like sometimes you'll see people talk about MSE, so that's the mean squared error. Sometimes you'll see RMSE, that's the root mean squared error. So since I've got a square root at the front, this is the square root mean squared error. So we have a loss. So now all we need to do is use gradient descent to try to modify our weight matrices to make that loss smaller. So Excel will do that for me. I have it installed. So it's probably worth knowing how to do that. So we have to install add-ins. Solve is there. Okay, let's see where it was. Oh, yeah. Okay, so the gradient descent solver in Excel is called Solver, and it just does normal gradient descent. So you just go Data, Solver, and you just make sure that in your settings that you've enabled the Solver extension that comes with Excel. And all you need to do is say, which cell represents my loss function? So there it is, V41, right? So where is your loss function stored? Which cells contain your variables, right? And so you can see here I've got H19 to V23, which is up here, and V25 to F39, which is over there. And then you can just say, okay, set your loss function to a minimum by changing those cells, and solve.
Wow.
And you can see the starts at 2.81, and you can see the numbers going down. And so all that's doing is using gradient descent exactly the same way that we did when we did it manually in the notebook the other day. Okay, but it's rather than solving the mean squared error for A at B in the A at X in the.
Wait, okay, I had no idea you could do that in Excel. Gradient descent? Really? It's just doing the gradient descent that we used to before, using the FastAI library. But in theory, something you could do using just pure Python, right? And it's just doing it directly. That's awesome.
Python, instead, it is solving the loss function here, which is the mean squared error with the dot product of each of those vectors by each of these vectors. So there it goes. So we'll let that run for a little while and see what happens. But basically, in Micro, here is a simple way of creating a neural network, because really in this case it's like just a single linear layer with gradient descent to solve a collaborative filtering problem. So let's go back and see what we do over here. So over here, we used getCollabLearner. Okay, so the function that was called in the notebook was getCollabLearner. And so as you dig deeper into deep learning, one of the really good ways to dig deeper into deep learning is to dig into the FastAI source code and see what's going on. And so if you're going to be able to do that, you need to know how to use your editor well enough to dig through the source code. Right? And basically, there's two main things you need to know how to do. One is to jump to a particular symbol, like a particular class or function by its name. And the other is that when you're looking at a particular symbol, to be able to jump to its implementation. So for example, in this case, I want to find getCollabLearner. So in most editors, including one I use, Vim, you can set it up so that you can kind of hit tab or something, and it jumps through all the possible completions, and you can hit enter, and it jumps straight to the definition for you. Right? So here is the definition of getCollabLearner. And as you can see, it's pretty small, as these things tend to be. And the key, in this case, it kind of wraps a data frame and automatically creates a data bunch for you because it's so simple. But the key thing it does then is to create a model of a particular kind, which is an embedding.bias model passing in the various things you asked for. So you want to find out in your editor how you jump to the definition of that, which in Vim, you just hit Control right square bracket. And here is the definition of embedding.bias. And so now we have everything on screen at once. And as you can see, there's not much going on. So the models that are being created for you by FastAI are actually PyTorch models. And a PyTorch model is called an nn.module. That's the name in PyTorch of their models. It's a little more nuanced than that, but it's a good starting point for now. And when a PyTorch nn.module is run, when you calculate the value, the result of that layer or neural net or whatever, specifically, it always calls a method for you called forward. So it's in here that you get to find out how this thing is actually calculated. When the model is built at the start, it calls this thing called __init__. And as I think we briefly mentioned before, in Python, people tend to call this dunder init, _init. So dunder init is how we create the model, and forward is how we run the model. One thing, if you're watching carefully, you might notice is there's nothing here saying how to calculate the gradients of the model, and that's because PyTorch does it for us. Okay, so you only have to tell it how to calculate the output of your model, and PyTorch will go ahead and calculate the gradients for you. And so in this case, the model contains a set of weights for a user, a set of weights for an item, a set of biases for a user, a set of biases for an item, and each one of those is coming from this thing called getEmbedding. So let's see getEmbedding. So here is the definition of getEmbedding, and all it does basically is it calls this PyTorch thing called nn.embedding. So in PyTorch, they have a lot of like standard neural network layers set up for you. So it's an embedding, and then this thing here is, it just randomizes it. So this is something which creates normal random numbers for the embedding. So what's an embedding? An embedding, not surprisingly, is a matrix of weights. Specifically, it's a matrix of weights. Specifically, an embedding is a matrix of weights that looks something like this. It's a matrix of weights which you can basically look up into and grab one item out of it. Right? So basically, any kind of weight matrix, and we're going to be digging into this in a lot more detail in the coming lessons, but an embedding matrix is just a weight matrix that is designed to be something that you kind of index into it as an array and grab one vector out of it. Right? That's what an embedding matrix is. And so in our case, we have an embedding matrix for a user and an embedding matrix for a movie. And here, we have been taking the product of them. Right? But if you think about it, that's not quite enough, because we're missing this idea that, like, maybe there are certain movies that everybody likes more. Maybe there are some users that just tend to like movies more. Right? So I don't really just want to multiply these two vectors together, but I really want to add a single number of, like, how popular is this movie, and add a single number of, like, how much does this user like movies in general. So those are called bias terms. Remember how I said, like, there's this kind of idea of, like, bias, and the way we dealt with that in our gradient descent notebook was we added a column of ones. Okay? But what we tend to do in practice is we actually explicitly say, I want to add a bias term. So we don't just want to have prediction equals dot product of these two things. We want to say it's the dot product of those two things plus a bias term for a movie plus a bias term for user ID. So that's basically what happens. When we set up the model, we set up the embedding matrix for the users and the embedding matrix for the items, and then we also set up the bias vector for the users and bias vector for the items. And then when we calculate the model, we literally just multiply the two together, just like we did. Right? We just take that product, call it dot, right, and then we add the bias, and then putting aside the min and max score for a moment, that's what we return. So you can see that our model is literally doing what we did here, with the tweak that we're also adding a bias. Right? So it's an incredibly simple linear model. And for these kind of collaborative filtering problems, this kind of simple linear model actually tends to work pretty well. And then there's one tweak that we do at the end, which is that in our case, we said that there's a min score of 0 and max score of 5. And so here's something to point out. So if you have arrange, so you do that dot product and you add on the two biases, and that gives you, that can give you any possible number along the number line, from very negative through to very positive numbers. But we know that we always want to end up with a number between 0 and 5. So that's 5. Or since it's 0. So what if we mapped that number line like so, this function? Okay, and so the shape of that function is
sigmoid. Yeah.
Right? And so it's going to asymptote to 5, and it's going to asymptote to 0. And so that way, whatever number comes out of our dot product and adding the biases, if we then stick to this function, it's never going to be higher than 5, never going to be smaller than 0. Now, strictly speaking, that's not necessary, right? Because our parameters could learn a set of weights that gives about the right number, right? So why would we do this extra thing if it's not necessary? Well, the reason is we want to make life as easy for our model as possible. So if we actually set it up so it's impossible for it to ever predict too much or ever predict too little, then it can spend more of its weights predicting the thing we care about, just deciding who's going to like what movie. So this is an idea we're going to keep coming back to when it comes to making, and it can spend more of its. Why would we do this extra thing if it's not necessary? Well, the reason is we want to make life as easy for our model as possible. So if we actually set it up so it's impossible for it to ever predict too much or ever predict too little, then it can spend more of its weights predicting the thing we care about, just deciding who's going to like what movie. So this is an idea we're going to keep coming back to when it comes to making neural networks work better. Is it's about all these little decisions that we make to basically make it easier for the network to learn the right thing. So that's the last tweak here, which is we take the result of this dot product plus biases, we put it through a sigmoid, and so a sigmoid is just a function that's basically 1 over 1 plus e to the x. The definition doesn't much matter, but it just has the shape that I just mentioned. And that goes between 0 and 1. And if you then multiply that by max minus min plus min, then that's going to give you something that's between min score and max score. So that means that this tiny little neural network, and it's a push to call it a neural network, but it is. It's a neural network with one weight matrix and no nonlinearities, so it's kind of the world's most boring neural network, with a sigmoid at the end. That's actually, because it does have a nonlinearity. The sigmoid at the end is the nonlinearity. It only has one layer of weights. That actually turns out to give close to state-of-the-art performance. I've looked up online to find out what are the best results people have on this MovieLens 100K database, and the results I get from this little thing are better than any of the results I can find from the standard commercial products that you can download that are specialized for this. And the trick seems to be that adding this little sigmoid makes a big difference. And did you have a question?
There was a question about how you set up your Vim, and I've already linked here about VimRC, but I wanted to know if you had more to say about that.
What do they want to know about Vim?
They really like your setup.
You like my setup? There's almost nothing in my setup. It's pretty bare, honestly. Whatever you're doing through editor, you probably want it to look like this, which is like when you've got a class that you're not currently working on, it should be this is called folded. This is called folded, right? It should be closed up so you can't see it. And so you basically want something where it's easy to close and open fold. So Vim already does all this for you. And then, as I mentioned, you also want something where you can kind of jump to the definition of things, which in Vim it's called using tags. So if you jump to the definition of learner. Basically, Vim already does all this for you. You just have to read instructions. Like VimRC is minimal, like basically how to use any extensions or anything. Another great editor uses VS Code, Visual Studio Code. It's free and it's awesome, and it has all the same features that you're seeing that Vim does. Basically, VS Code does all of those things as well. I quite like using Vim because I can use it on the remote machine and play around. But you can, of course, just clone Git onto your the Git repo on your local computer and open it up in VS Code to play around with it. Just don't try and look through the code just on GitHub or something. That's going to drive you crazy. You need to be able to open it and close it and jump back. Maybe people can create some threads on the forum for Vim tips, VS Code tips, Sublime tips, whatever. For me, I would say if you're going to pick an editor, if you want to use something on your local, I would go with VS Code today. I think it's the best. If you want to use something on the terminal side, I would go with Vim or Emacs. To me, they're clear. So what I wanted to close with today is to kind of take this collaborative filtering example and describe how we're going to build on top of it for the next 3 lessons to create the more complex neural networks we've been seeing. And so, roughly speaking, this is the bunch of concepts that we need to learn about. Let's think about what happens when you're using a CNN or whatever, a neural network to do image recognition. Basically, let's take a single pixel, right? You've got lots of pixels, but let's take a single pixel. So you've got a red, a green, and blue pixel. Okay, and so each one of those is some number between 0 and 255. Or we kind of normalize them so they're floating point between, with a mean of 0 and standard deviation of 1. But let's just do them, let's say whatever they're like. Do the 0 to 255 version, so it's like 10, 20, 30, whatever. Okay. So what do we do with these? Well, what we do is we basically treat that as a vector, and we multiply it by a matrix. Right? So this matrix, depending on how you think of the rows and the columns, let's treat the matrix as having 3 rows, and then how many columns? Well, you get to pick. Right? You get to pick, just like with the collaborative filtering version, I decided to pick a vector of size 5 for each of my embedding vectors, right? So that means that's an embedding basically of size 5. Right? You can get to pick how big your weight matrix is, so let's make it size 5. Okay, so this is 3 by 5. So initially, this weight matrix contains random numbers. Remember when we looked up getting embedding matrix just now, and there were 2 lines. The first line was I create the matrix, and the second was fill out the random numbers. That's what we do, right? I mean, log it's hidden behind the scenes like FastAI and PyTorch. That's all it's doing. So it's creating a matrix of random numbers when you set it up, and the number of rows has to be 3 to match the input, and the number of columns can be as big as you like. And so if you multiply the vector, the input vector, by that weight matrix, you're going to end up with a vector of size 5. So people often ask, how much linear algebra do I need to know to be able to do deep learning? This is the amount you need, right? So, and if you're not familiar with this, that's fine. You need to know about matrix products. Okay, you don't need to know a lot about them. You just need to know, computationally, what are they, what do they do, and you've got to be very comfortable with, if a matrix of size blah times a matrix of size blah gives a matrix of size blah. How do the dimensions match up? So if you have 3 And remember, in NumPy and PyTorch, we use at times 3 by 5 gives a vector of size 5. Okay. And then what happens next? It goes through an activation function, such as ReLU, which is just max 0, x, and spits out a new vector, which is, of course, going to be exactly the same size, because no activation function changes the size. Right? It only changes the contents, so that's still size 5. What happens next? We multiply by another matrix. And again, it can be any number of columns, but the number of rows has to map nicely, so it's going to be 5 by whatever. 1, 2, 4. So maybe this one has, 5, say by 10. And so that's going to give some output, which will be size 10. And again, we put that through ReLU. And again, that gives us something of the same size. Okay. And then we can put that through another matrix. Actually, just to make this a bit clearer, you'll see why in a moment. I'm going to use 8, not 10. So that these. Let's say we're doing digit recognition, right? So there are 10 possible digits. So my last weight matrix has to be 10 in size, because then that's going to be my final output is a vector of 10 in size. And remember, if we're doing like digit recognition, what happens? We take our actuals, right?
Argmax, I think.
Which is 10 in size. And like if the number that we're trying to predict was the number 3, that's the thing we're trying to predict, then that means that there is a 3, 0, 0, 0 in the third position. Right? So what happens is our neural net runs along, right, starting with our input, and going weight matrix, ReLU, weight matrix, final output, and then we compare these two together to see how close they are, how close they match using some loss function. We'll learn about all the loss functions that we use next week. But now the only one we've learned is mean squared error. And yeah, we compare the actual, we can think of them as probabilities for each of the 10 to the actual each of the 10 to get the loss, and then we find the gradients of every one of the weight matrices with respect to that, and we update the weight matrices. So the main thing I wanted to show right now is the terminology we use, because it's really important. These things contain numbers. Specifically, they initially are matrices containing random numbers. And we can refer to these yellow things as, in PyTorch, they're called parameters. Sometimes we'll refer to them as weights, although weights is slightly less accurate because they can also be biases, right? But, we kind of use the terms a little bit interchangeably, but strictly speaking, we should call them parameters. And then after each of those matrix products, that calculates a vector of numbers. So here are some numbers that are calculated by, here's some numbers that are calculated by a weight matrix multiplied. And then there's another set of numbers that are calculated as a result of a ReLU, as a result of the activation function. Okay? Either one is are called activations. So activations and parameters both refer to numbers. Right? They are numbers. But parameters are numbers that are stored. They're used to make a calculation. Activations are the result of a calculation. They're numbers that are calculated.
Okay.
Right? So they're the two key things you need to remember. So use these terms, right? And use them correctly and accurately. Right? And if you read these terms, they mean these very specific things. So don't mix them up in your head. And remember, they're nothing weird and magical. They're very simple things. An activation is the result of either a matrix multiply or an activation function. Okay? And a parameter of numbers inside the weights, inside the matrices that we multiply by. Okay? That's it. And then there are some special layers. So every one of these things that does a calculation, all of these things that does a calculation, are all called layers. They're layers of our neural net. So every layer results in a set of activations because there's a calculation that results in a set of results. Okay? There's a special layer at the start, which is called the input layer. And then at the end, you just have a set of activations. Okay? And we can refer to those special, they're not special mathematically, but they're semantically special. We can call those the outputs. Right? So the important point to realize here is the outputs of a neural net are not actually like mathematically special, they're just the activations of a layer. And so what we did in our collaborative filtering example, we did something interesting. We actually added an additional activation function right at the very end. Right? We added an extra activation function, which was sigmoid. Specifically, it was a scaled sigmoid between 0 and 5. Right? And that's really common. Right? It's very common to have an activation function as your last layer, and it's almost never going to be a ReLU, because it's very unlikely that what you actually want is something that stops at the truncates at 0. It's very often going to be a sigmoid or something similar, because it's very likely that actually what you want is something that's between two values. Okay, kind of scaled in that way. So that's nearly it, right? So we've got inputs, weights, activations, activation functions, which we sometimes call nonlinearities, output, and then the function that compares those two things together, right, is called the loss function, which so far we've used MSE.
Okay.
Yeah, okay, and that's enough for today. So what we're going to do next week is we're going to add in a few more extra bits, which is we're going to learn the loss function that's used for classification, which is called cross entropy. We're going to use the activation function that's used for single label classification, which is called softmax, and we're also going to learn exactly what happens when we do fine tuning in terms of how these layers actually, what happens with unfreeze and what happens when we create transfer learning. So thanks everybody. Looking forward to seeing you next week.
All right, that was actually pretty simple. I like that overview. I like how simple that overview was. Like he goes through, I've seen all of these terms, of course, parameters, activations, ReLU, and all that stuff. But just seeing the big picture here, sigmoid at the end, really helps, because encountering all of these things individually just makes you think like there's this entire forest that you'll never be able to wrap your head around. But just seeing everything, all of our suspects lined up like this, makes it a lot easier just to understand the vocab once, and then be able to read through any sort of material. Now, obviously, there's going to be other stuff like Yeah, I know. Okay, so sigmoid. There's also softmax, and there are all sorts of crazy, what do they call them? Activations, right? Since we're using the lingo here, so all sorts of crazy activations. But we don't like. We just know generally. Okay, they fit into this bucket called activations. Well, anyway, that's enough for now. The results are in. I'm going to run these in another video because I know this is going to take a while. I'll run this in another video, and then I'll share the results, and we'll just spend an entire video going through these results. So that said, thank you very much for tuning in, ladies and gents. I hope you guys have a wonderful day. Adios.